Good afternoon, everyone. My name is Rajat Boni. I am one of the PMRF research scholar at IITSM Hadlar, and today is week 10 of this foundation engineering course. I am one of the TA of this course, and this course is conducted by Professor Dilip Kumar Buddha sir. I have also uh, 6 months teaching experience in Nptel on ground improvement course, which is conducted by Professor Dilip Kumar Vaidya sir. Now, in week 10, we of this foundation engineering course, we discuss the further things of about this deep foundation. We already covered the deep foundation of different types of deep foundation and why it is used, and also we studied the single file foundation as a deep foundation, also group group of file foundation as a deep foundation. Now today's class we discuss about the quick tense lectures one by one, and in this quick 10 here we discuss the another type of deep foundation, which is sheet pipe foundation, which are mostly used in the offshore uh, to protect the shore side from the wave of uh, ocean water. So let's start our today's session. And one or two things I want to mention here, that this class this class is recorded and it will be shared to everyone from my YouTube channel. And also, whatever I am discussing here, whatever the materials I am discussing, it will be shared to everyone through Google Drive. So don't worry. And if there is an issue in network or I am disconnected due to the network problem, don't worry. I will try to resolve the problem and rejoin the lecture. So don't leave the lecture. So today uh, we in week uh, 10, before discussing the week 10, we first discuss the previous classes of deep foundation because it is require the knowledge of this of this previous class, and also after that I study the I will teach you the week 10 lectures. After that, we try to solve the previous year question and also try to solve some book exercise problem about this today's class. So let's start our today's session. I am sharing my screen. Actually, I am conducting my session in my mobile. So hopefully it will be shared to everyone. So please stay on the line. I'm sharing. I think it is visible to everyone. So before discussing the previous classes, we quickly revise the before discussing today's class, we quickly revise the previous classes of deep foundation very quickly. So I think my screen is visible to everyone. So in previous class, we start with the pile foundation. So we studied the classification, different classification of the foundation, which is shallow foundation, deep foundation, and we studied the shallow foundation is less expensive and better for lighter structure, but less in also less problematic soil. A deep foundation is require more expensive and typically used for heavy tall structure and used mostly on problematic soil. So then we discuss the design requirement of this deep foundation. So so main requirement is safety. Then we use mainly foundation for serviceability. So safety related to the safety against the shear failure or shear failure or bearing capacity failure of the soil. Serviceability mostly deals with the settlement of the structure, whether it is immediate settlement, whether it is consolidation or secondary consolidation settlement, primary and secondary consolidation settlement. Then another term we call the allowable bearing capacity, which is the maximum load that satisfies the both. That means satisfy the adequate satisfy the safety and also satisfy the serviceability. Then what are the use of the deep foundation? When we use mostly the deep foundation, it is mostly used when the soil is when the foundation is more expensive and used to get acceptable bearing capacity and settlement, and typically mm, used for larger structure or more problematic soil. Now, why we need this deep foundation? So the deep foundation is required. We study the field or poor soil condition if they are near the surface. So excavation of this for footing foundation would be difficult. Then we use this deep foundation. And again, if the ground permeability and groundwater condition is likely to make it difficult and expensive to exclude the water from the excavation, then we also use the deep foundation. Then to get acceptable bearing capacity, which may be difficult to achieve by footing uh, shallow foundation, then we also use the deep foundation to keep the settlement within the acceptable limit, which may be difficult to achieve in footing foundation. Foundation to carry heavy column load. So these are the factors we to address uh, by choosing the deep foundation. Now there is different types of deep foundation: pile, drill, piers, and cushion. We already studied. So functionally, a functional features are similar. Is typically subjected to an axial load. Sometimes piles and caissons serve as anchors for partial installation. Difference is primary in their physical size and method of installation. Now piles. And piles are specially installed relatively slender columns used to transmit structural load to a lower, firmer soil or rock formation. Diameter is generally less than 750 mm. The pile may be of concrete, steel, timber, or a composite of steel and concrete. Drill piers or caissson piers. In generally, drill piers and caissson piers are larger piles, usually 750 mm or more in diameter. The term drill piers and caisson are frequently used interchangeably by engineers. For drill piers, typically a shaft is drilled into the soil, which is then filled with concrete. The shaft may be cased with a metal shell in order to maintain the shaft from collapsing. The casing may be left in the place as a part of the pier, or it may be gradually withdrawn as the shaft is filled concrete. The lower part of the shaft may be uncut or bell out to develop a larger end bearing area, thereby increasing the capacity of the pier. Typically, drill piers and caissons are designed as end bearing members. Now, classification of pile foundation based on material. So there are four types of pile. One is timber piles, another one is steel pile, concrete pile, and composite pile. Composite means we use both steel and timber concrete to construct the pile. Now, then we discuss now we use material selection criteria to uh, choose the material of this pile foundation. So material should be corrosive property of the stratum. To choose the material, it should be need to check the corrosive property of the stratum. Also check the fluctuation in water table. Then ease of installation, length of the foundation, the pile foundation, availability of material, installation equipment, and restriction in driving noise and vibration and cost. We need to check by while choosing this material for pile foundation. Then customary design loads for piles for different types of material using for pile foundation. If you use wood, then the uh, load it will take axial load it will take in between 15 to 30 tons. If you use composite material, that is a composite of steel and concrete, then we the load is in between 20 to 30 ton. Then there are different types of pile foundation like cast in place concrete, precast reinforced concrete, steel pipe concrete, steel edge section like this. And this table it denotes the different types of load it will take different loads it will take based on the defined material. Now there is the maximum available length for this different types of material. If you use the steel edge and pipe type of pile, then we can use only limited length of pipe, and the short section are driven and the additional section are filled welded to obtain the desired length. If you use the steel shell and cast in place type pile, then the length is in between the 100 to 125 foot. If you use precast concrete pile, then the solid small cross section is up to 60 foot and large diameter cylindrical pile can be up to 200 feet long. The cast in place concrete, if you use, then the length is in between 50 to 75 feet. And if you use bulb type cast in place concrete, then the length is up to 100 feet. Like this, there are composite. If you use composite, then the maximum length is up to 150 foot. And if you use timber, depends on the wood type, usually 50 to 60 foot. And limited quantity is 75 foot and up to 100 foot possible, but very limited. Now, classification of the pile foundation based on the function. So it is based on the function. The types are end bearing piles, friction piles, tension or uplift piles, compaction pile, anchor piles, batter pile, and lateral loaded pile and sheet piles. These are the pictures or pictorial figure form of these different types of pile. You can go through it. We already discussed it. Uh, then classification pile based on we study the classification pile based on the installation. There are two types: driven piles and casting sheet pile. So driven piles mostly installed by. So pile installation method are match by group condition and driving device. So these are the methods. So pile driven pile, most common method, and it use steam hammer, diesel hammer, and vibratory hammer to driven the pile. Like jet driven pile, of- where where force water before pile to ease the placement. So like that, there are other pile, uh, other used for the cast in place and to drill through the obstacles like that. So maximum driven resistance for timber piles. If you driven the timber piles, then the resistance should be maximum resistance should be 4 to 5 blows per inch. If you use concrete, then the resistance is 6 to 8 blows per inch. If you use concrete, then the maximum blows is 12 to 15 blows per inch. Then pile capacity. For single pile capacity and pile in group, what is the capacity? So for single pile, we use friction pile and bearing pile and both friction and bearing pile. So these are the here it is given the load transfer mechanism of this single pile through skin friction and also end bearing. So the total ultimate load of a single pile is total load taken by the skin friction plus total load taken by the end bearing. And if you use if you find out the allowable capacity, then we have to divide this ultimate load by factor of safety. So here is given the total load taken by the skin friction is Fs into As, where Fs is the skin friction resistance and A is the surface area of the shaft. Where total load taken by the end bear ring is the Ft into At, where Ft is the tip resistance and of this and At is the bearing area or cross sectional area of the part. Moving to the lecture number 39 on previous classes. Here we detail elaborately find out uh, the load transfer mechanism of the pipe. So now first we find out the total ultimate load for a pile driven in cell. So total load is summation of the friction capacity and end bearing capacity. So the friction capacity is F into a surface, where F can be evaluated by multiplying the coefficient of friction between sand and pile surface, that is tan delta, by the total horizontal soil pressure acting on the pile. And where we use material tan delta is 0.45 concrete for concrete 0.45 If you use wood, then tan delta is zero point 0.4. If you use steel, then tan delta is 0.20. If you use corrugated steel, then tan delta is 10.5 of sand. Then there is one note is given, that is horizontal soil pressure. That is, total horizontal soil pressure acting on a pile is the function of effective vertical pressure of the soil adjacent to the pile. The soil pressure normally increases as the depth increases. However, it has been determined that the effective vertical pressure of soil adjacent to a pile does not increase without limit as the depth increases. Instead of effective vertical pressure increase as the depth increase until a certain depth of penetration is reached. Below this depth, which is called the critical depth and denoted as a DC, effective vertical pressure remains more or less constant. So you see that there is a one term critical depth. This means as the depth increase, the effective vertical increase. But after a certain depth, the effective vertical depth remains constant, and this depth limiting depth is called critical depth. There is it is by the help of this diagram you can easily understand the concept of the critical depth. So we see that as the depth increase, the effective vertical stress also increase linearly. But after a certain depth DC, which is called a critical depth, the effective vertical stress remain constant. There is no change. So this depth from the ground surface is called critical depth. From where the effective vertical depth become constant. Now, there is one formula is given for this uh, to find out the skin friction. So you see that total skin load is gamma dc square by 2 plus L minus dc into gamma dc whole into K tan delta pi, where K is the coefficient of active earth pressure, D is the diameter of the pipe, L is the length of the pipe, and this is the critical depth. Now find out the total tip load. So which is equal to the Q into A tip, where Q is equal to the, if you consider as a shallow foundation, a circular shallow foundation, a square shell foundation, it is equal to the gamma df nq plus zero point 0.3 gamma d n gamma for circular pipes and gamma df nq plus zero point 0.4 gamma b n gamma for square pipe. Now here it is said that we consider the formula as a this whole formula as a q into q sigma v t uh, into nq. Uh, because there is a little change, we can consider it is fine that this gamma into df nothing but the empty shape at the tip. So, and nq is the bearing capacity uh, coefficient. So, approximately we said that q is equal to sigma v at tip into nq. Now, moving to the lecture number 40, or I think 30, 40. Now, here is the total capacity uh, of this circular pipe given in sand is equal to the gamma dc square by 2 plus L by the dc into gamma dc into k tan delta into pi d plus gamma dc nq star whole into pi d square by 4. Now moving to the uh, pile capacity or given pile capacity for in clay. So same in clay, the friction load is equal to the alpha into C into a surface, where alpha is the adhesion coefficient, and C is the unit coefficient of the shaft around the shaft, and a surface is nothing but the surface area of the shaft or pipe. And then the QT, and here it is said that if this adhesion factor is for soft clay is equal to 1, and in stiff clay it is less than 1. And now to find out the total tip load, which is equal to the Q into A tip, where Q is the CNC gamma df, which is approximately CNC, and NC is equal to 5.14 for shallow foundation, but deep foundation it is 9. So here CNC is equal to the 9 into C for clay driven pipe in core. Now here total capacity for circular pile in driven in clay is equal to the Q is equal to the alpha C NC into pi dl plus CNC pi d square by 4. And now there is a load transfer curve around the pile. It is shown. Different as a curve are here. Can go through it. We already discussed. Then then we discussed the test file for finding the found out the pile capacity by conducting test a resemble test of pile foundation on the same soil where the construction will be done. So the test file is used to testing the or pile foundation or to find out the uh, design pile load by conducting the uh, pile test. So one, sometimes more than one of for bigger project of the design piles on which the load tests are carried out to use. Normally piles are designed initially by analytic or other method based on estimation load and soil characteristics. The pile load tests are performed on the test pile during the design stage to check the design capacity. The result from the pile test would be the source of the most useful information in a least general aspect result in determining the ultimate bearing capacity of the pile, in evaluating the deflection characteristics of the pile. With regard to the ultimate bearing capacity or expected settlement, One may reflect on several additional and tangential benefits. For example, if the capacity of the pipe is different or settlement is excessive from that desired, the pile length, pile diameter, and details of installation can be adjusted prior to the installation of the rest of the pipe. A side but eventually important benefit from the installation and testing of a pipe prior to the installation of the rest is general information about the site condition with regard to the potential problem which may or may not be fully reflected in prior soil surface investigation. Though the pile load test is the most reliable means of determining the load capacity of the pile or estimating settlement, one should not assume that load tests are unquestionably accurate. The test results may be misleading if the relevant factors are overlooked. So these are the here one file load test elements is given, and I use the loading frame for hydraulic jack, which is given the load on the pile test pile, and there is a load cell to measure the load, and there is dial rods to measure the deformation. All tip displacement. There is another arrangement, more precise arrangement of these test piles. So these are about the test file or pilot test. Now we discuss the file capacity in groups. That means files in group we discuss. So the behavior of a group of files is different from that of individual files in a number of ways. In general, carrying capacity of the group of files is less than the sum of the capacity of the individual file. The settlement of a pile group is larger than that of the individual piles for a corresponding level of loading. The efficiency of the pile group is less than that of the single pile. Piles in a group interact with each other. The effect depends on the soil, the head fixity condition, and the configuration. In spite of these shortcomings, the pile group is a much more common occurrence than a single pile. Single pile lack the overall stability against overturning, a deficiency that is easily overcome by a cluster of piles. For column, a minimum of two piles, but more commonly, three or more piles are clustered in a group and connected by a concrete cap to form a unit. For walls, a line of single piles is common. These are the different arrangement of this uh, group of piles. There are in three piles you use, four pile, five piles, six piles. So these are the different arrangement for different number of piles. We can use more number of piles as our requirement. Now there is efficiency of group piles. So efficiency group piles is denoted by nika is equal to the total efficiency group file divided by the number of piles in a group into the total load of a or capacity of a single individual pile. If we use the end bearing piles, efficiency is equal to 1, we assume. If you use friction pile given in portionless soil, the efficiency is equal to 1, we assume. If a pile is composed of friction driven pile in cohesive soil, the efficiency is less than 1, we assume. There is another way to find out the efficiency of the group of pile. which is given by the converse lever equation, and which is equal to the 1 minus theta n minus 1 into n plus m minus 1 into n divided by 90 mm, where n is the number of piles in a row, where n is the m is the number of rows in pile. D is the diameter of pile, S is the spacing of the piles, center to center spacing. For friction pile remaining in cohesive soil, Cole and Soliman suggested that the group pile group efficiency may be assumed very linearly from a value of zero point 0.7 at the pile facing of 3 times the diameter to the value of 1 at the pile facing 8 times of the pile diameter. There is a problem in this lecture. We will discuss in later sessions. Now, pile foundation for facing pile facing less than 3 times the pile diameter in clay, the group capacity may be considered as a block capacity, and the total capacity can be estimated by treating a group as a pair. And this formula is used if the spacing is less than the 3 times of the pile diameter in clay in cohesive soil. That means if spacing is less than 3 times the pile diameter in clay, we use as a failure as a block failure. For pile spacing less than 3 times the pile diameter, the group capacity can be obtained applying this formula. Qg is equal to 2D into W plus L into F plus 1.3 C and C WL. D is the depth of the group, W is the width of the pile group, L is the length of the pile group. F is the unit addition developed between the cohesive soil and the pile surface, which is equal to alpha into C. C is the cohesion or hardened strength of the soil, and C is the bearing capacity factor. Shallow foundation footing, it is 5.14. For deep foundation, it is 9. Now, so and there is another type of failure, which is individual failure in group. So individual failure in group, you can find out by summation of the total load taken by the individual piles. That is n into the total load of capacity of an individual pile. And the capacity in clay, group capacity, pile group capacity in clay is the minimum of these two. That is n into summation of q into so n not n. It is efficiency meter into summation of q into a or u block. Now settlement, pile settlement. So please so there are three types of pile settlement. The elastic pile settlement of the pile, Settlement of the pile caused by the load at the pile tip, and settlement of the pile caused by the load transmitted along the pile shaft. So settlement, elastic settlement of the pile, that is S1 is equal to the QWP as epsilon QWS into L divided by AP into EP. QWP is the load carried at the pile point under working load condition, and QWS is the load carried by the friction resistance under the working load condition. Epsilon is the magnitude which depends on the nature of unit friction resistance distributed along the pile shaft. L is the length of the pile. It is the unit modulus of the elasticity. Modulus elasticity of the pile material. It is the area of the pile cross section. S2 is equal to the QWP into D divided by ES into 1 minus mu S square into IWP. QWP is the point load per unit area at the pile point, which is equal to QWP, capital QWP by AP, and D is the width or diameter of the pile. ES is the unit modulus of the soil. Mu S is the poison ratio of the soil. IWP is the express section, which is after R. Then there is another type of settlement which is to the S3, which is to QWS divided by P into L and into D by ES into 1 minus mu S square into IWS. So IWS is the sector, P is the perimeter of the pipe, and L is the amendment length of the pipe, QWS is the section resistance of the pipe. IWS is the 2 plus 0.35 into root over L by D. Now there is another type of settlement which is depends on the consideration of the soil or consideration settlement. Uh, it is said that piles in uniform soil supported from friction and end bearing, and if you use then assume the equivalent draft at 2 by 3 of the pile embedment length from the surface. So here it is equal to this same thing is which is as we study in consolidation settlement, which is equal to del H is equal to the CC into H1 over 1 plus C1 log 10 P1 plus del sigma divided by sigma 1. But if you use this arrangement in a firmer strata or more compact strata, then this equivalent graph is at the pile tip. And formula is same. That means whole calculation is we done from the pile tip. So I think previous classes discussion has covered. Now we uh, discuss today's that means week 10 lectures. And before discussing the week 10 lectures, we now take a small break. After that, we start our lectures again. So please stay on the line, and I will join after 5 or 6 minutes. You can stay on the line. Hello, hello. Hello. Mhm. So, hmm, so there is a network problem. Hmm, 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 hmm. Okay. Hmm. See, the problem is usual. So now we start our session again, and I'm sharing my screen again. So please wait. Now we discuss about the another type of deep foundation, which is called sheet pile foundation or sheet pile wall. So sheet pile walls. Sorry, please. The sheet pile walls. The sheet pile walls consist of continuously interlocked pile segments embedded into in soil to resist the lateral pressure. Classified as a flexible retaining system, sheet pile walls can tolerate relatively large deformation. So these are the arrangement of sheet piles in C D. So to better understand, we we move on to book, which is of author is VNS Murthy. So sheet pile. So sheet pile walls are retaining walls constructed to retain earth, water, or any other fill materials, and mostly used for waterfall structure, for example, in building, rough, quay, and piers. Building that as also used as a building dimension dam, such as coffer dam, and also used as a river bank protection, and also used as a retaining the site and cuts mill. So you can see that there is different types of sheet piles, uh, straight sheet piling, shallow arc web filing, arc web filing, and sheet file section. The most common types of files used are steel sheet files. The steel sheet file possesses several advantages about the other types. Some important advantages is that they are resistant to high driving stresses as developed in hard or rocky material. They are lighter in section. They may be used several times. They can be used either below or above the water or possess longer life. Suitable joints which do not deform during driving can be provided to have a continuous work. The pile length can be increased either by welding or bolting. Now, sheet pile structures. So there are different types of sheet pile structure. They are as a cantilever sheet pile, anchor bulkheads, raised sheeting in carts, single cell cofferdam, cellular cofferdam, circular type cellular cofferdam, diaphragm. Now, so we can see that there are different types of sheet piles. Figures are given. The first one is cantilever sheet pile. So it is act as a cantilever. One side is water table present, water structure like river front, dam like this. And the one is backfill material. There is another is anchor bulkhead sheet pile. Then there is bed sheeting in carts. Then single cell coffer dam. Then circular coffer dam and circular cellular coffer dam. Diaphragm types and double sheet pile walls. Now free cantilever sheet pile wall. So when the height of the earth to be retained by sheet piling is small, the piling acts as a cantilever. The force acting on the sheet pile was include the active earth pressure on the back to the wall, which tries to push the wall away from the backfill. Then passive pressure in front of the wall below the dredge line. The passive pressure resists the movement of the wall. The active and passive pressure distribution of the wall are assumed hydraulic in the design of the wall, although the Coulomb approach considers the friction tends to be more realistic. The Rankine approach is normally used. The pressure due to the water may be neglected if the water levels on the both sides of the wall are seen. The difference in the level is considerable. The effect of the difference on pressure will have to be considered. Effective unit weights of the soil should be considered in computing the active and passive pressure. Now there is the working mechanism or earth pressure on the sheet pile. You can see the figure A. If we apply lateral load, it is acting as a cantilever, and there is a so now So general principle of the design of the free cantilever sheet pipe. The action of the earth pressure against the cantilever sheet piling can be best illustrated by a simple case shown in figure 20.5a. So you can see that in case the sheet pile is assumed to be perfectly adhesive, so there is no deformation on the sheet pile, which is we consider as a perfectly rigid body. Then, when a horizontal force P is applied at the top of the piling, the upper portion of the piling tilts in the direction of P, and the lower portion moves in the opposite direction as shown by a dashed line in the figure A. Thus, the pile rotates about a stationary point O dash. The portion above O dash is subjected to a passive earth pressure from the soil on the left side of the piles and active earth pressure on the right side of the pile, whereas the lower portion of the O dash G O dash C is subjected to a passive earth pressure on the right and the active earth pressure on the left pile. At the point O dash, the pile does not move and therefore is subjected to an equal and opposing earth pressure. That is earth pressure at rest, with net pressure equal to zero. The net earth pressure, the difference between the passive and the active, is represented by O A B O dash C in figure B. A B O dash C. A B O dash C is the net earth pressure difference. For the purpose of the design, the curve VOC is replaced by straight line BC, and the point D is located at such a location on the line F that the sheet piling is in static equilibrium under the location action of force P. The arc pressure represented by the area of ADE and ECG. The position of the D can be determined by a trial and error method. This discussion leads to be the conclusion that cantilever sheet pile drive derives its stability from the passive earth pressure on the both sides of the piling. However, the distribution of the earth pressure is different between the sheet pile in granular soil and sheet pile in cohesive soil. The pressure distribution is likely to be changed with the time of sheet pile in field. So you can see that if we apply pressure and P in horizontal direction, there is a rotation is occur in the about the point of O. So the left side about above the O dash, The right side acts as active earth pressure and the left side acts as a passive earth pressure. And below the O point, O dash point, the right side acts as a passive earth pressure and left side is act as a active earth pressure of this sheet pipe, cantilever sheet pipe. But the actual pressure diagram is A, B, O dash C. But for the calculation purpose, the B O dash C replaced by the D E C, a straight line. Where the straight line D is the point where the uh, stability maintained. So and D point you should find by trial and error method. And and now the actual pressure diagram is A D E and E C G. So, and the both the case, the passive earth pressure is greater than the active earth pressure. Now there is different condition should be applied to find out the capacity of the cantilever sheet pile. So first is depth of embedment of the cantilever walls in sandy soil. And case one with water table at a greater depth. So there is no water table consideration of the water table. You can see that. So the active earth pressure acting on the back of the wall tries to move the wall away from the backfill. If the depth of the embedment is adequate, the wall rotates about its points or days, seated above the bottom of the wall as shown in figure 20.6a. The types of pressure acts on the wall when rotates is likely to take place about the point O dash R. There are different types of pressure X. These are active earth pressure at the back of the wall from the surface of the backfill down to the point of rotation O dash. The pressure is designated as PA1. Passive earth pressure in front of the wall from the point of rotation O dash to the ridge line. The pressure is designated as PP1. The active earth pressure in front of the wall from the point of rotation to the bottom of the wall. This pressure is designated PA2. The passive earth pressure at the back of the wall from the point of rotation O dash to the bottom of the wall. This pressure is designated as PP2. The pressure acting on the wall are shown in the figure. We can see that figure A. So we see that above the point O dash in left side, the pressure is active passive earth pressure. In the right hand side, it is active earth pressure, but it is opposite in about the point O dash, bottom of the point of O dash. So we see that figure A is shown the pressure acting on the cantilever sheet pan. Now the pressure acting on the wall shown in the figure paper, if the passive and active earth pressure is algebraically combined, the resultant pressure distribution below the dredge line will be given in the figure B, and the various notation are given. D is the minimum depth of embedment with the factor of safety equal to 1. K is the maximum depth of embedment Kp is the Rankine active earth pressure coefficient, Kp is the Rankine passive earth pressure coefficient, and K is the Kp minus Ka. Pa bar is the effective earth pressure acting against the sheet pile at the dredge line. Gamma H K. Pp bar is the passive earth pressure at the base of the pile while acting towards the backfill, which is equal to the gamma D naught K. So now go back to the figure. You can see that there is one line from BPA bar like this, and we can see that along the cantilever, along the cantilever sheet pile, there is a pressure distribution line is drawn, and it is in the right hand side. There is active earth pressure in the left hand side above the O point. It is passive earth pressure, and below the O point there is passive earth pressure in the right hand side and left hand side is active earth pressure. So you see that there is PA bar and there is PP bar about the result. So P dash P bar is equal to the effective earth pressure, effective passive earth pressure at the base of the sheet pile wall, acting is the backfill side of the wall, which is equal to PP double dash plus gamma K D naught. And then effective passive earth pressure at the level of O is equal to gamma Y naught K plus gamma H Kp, which is equal to the PP double dash one. Gamma is the effective unit rate of the soil, assumping the same below and above the dredge line. One is the depth of point O below the dredge line, where the effective and active pressure are equal. That is, net pressure is zero. Y bar is the height of point of application of the total active pressure PP above the O point, and H is the height of point P above the base of the wall. D naught is the height of the point O above the base of the wall. Now expression for Y naught is at the point of O, the passive pressure acting towards the right should be equal to the active pressure acting towards the left. So gamma Y naught Kp is equal to gamma plus H plus Y naught into K. Therefore, Y naught is equal to the Pa bar by gamma K. Now, expression for H for static equilibrium, the sum of the force of in the horizontal direction must be equal to zero. That is Pa minus half of Pp bar into D minus Y naught plus half of Pp bar plus half of P dash P bar into H is equal to zero. Solving and get the H. Now, taking moment of all forces about the bottom of the pipe and equating it to zero, we get to the expression of uh, PP bar and P dash P bar. and we get C1, C2, C3, C4 coefficient constants. Solution of this equation gives the depth of D now. The method is a trial and error and generally adopted to solve this equation. The minimum depth of embankment D with a factor of safety equal to 1. Therefore, D is equal to D naught plus 1. A minimum factor of safety of 1.522 may be obtained by increasing the minimum depth at D is equal by 20 to 40%. Then we find out the maximum bending moment. Maximum moment on the section AB is occur at the point of zero shear, and this point occurs below the point O in figure. That this point is presented by the point C at the depth of y naught bar below the point O. Net pressure is a triangle of O C C dash must be balanced. The net active pressure PPA acting above the dredge line. The equation for PA is PA is equal to half y naught square gamma Kp minus K, and y naught bar is equal to root over 2Pa by gamma K. Then find out the maximum moment and maximum section modulus, which is equal to the mx divided FD. FD is the allotted favorable stress of the sheet pipe. And there is another method of the simplified method, which is equal to the solution for the fourth degree of equation is quite laborious, and the problem can be simplified by assuming the pressurized pressure as a PP. If PP dash bar as a concentrated force are acting on the at the foot of the pipe, and the simplified arrangement as shown in the figure. You can see that. Now, for equilibrium, the moment of this active pressure on the high right and passive resistance on the left should about the point of reaction R must be balanced. Then 1/3 of ppb is equal to pa by 3 whole into h plus d is equal to 0, and get the pp, and we get the equation and find the d depth, which is at least a guide to required depth. The depth calculated should be increased by at least 20% to provide a factor of safety and to allow extra length to develop the passive pressure R. An approximate depth of embedment may be obtained from the table 20.1. You can see it. So the circulation should be from the dredge level, and from dredge level, this so for very loose and firm and dense, different D is given. That is, for very loose it is 2H, for loose it is 1.8, for firm it is 1H, for dense it is 0.75H. So I will come in after few minutes. Little break is required. So please stay on the line. Sorry for that. There is frequently disturb in my network because my I am doing my classes on my right. So now I am again share my screen, uh, discussing the sheet file without water table. Now we discuss about the sheet file with I think it is visible to everyone with water table within the back. So all the calculations are same, but there is a water table that is at H1 below the ground level. All the notations given in figure same as those in given previous figure. In this case, the soil above the water table is an effective unit of gamma and a saturated unit of gamma dead below the water table. A gamma set below the water table. And the submerged unit weight is gamma B. Now, active earth pressure at the water table is gamma H1 into K, and at the dredge line is gamma H1K plus gamma B H2K. And other expression are that is PP bar is equal to gamma B D naught K, P P dash bar is gamma PP double dash bar plus gamma B D naught K. So P double dash uh, PP double dash bar is equal to gamma B Y naught K plus gamma H1 plus gamma B H2 Kp. Y naught is equal to the P A bar by gamma B K. H is equal to the PP bar D minus gamma naught Y naught minus 2P PPT. Everything is same calculation is done, but there is a change in pressure diagram. So you go through this. Now for simplified method, now we try to solve one problem regarding to this, and these are the very big problem. So the question example 20.1. So determine the depth of amendment for sheet pile shown in figure example 21A by rigorous analysis. Determine also the minimum section modular. Assume an allowable fracture stress FB is equal to the 175 meganewton per meter square. The soil is an effective unit weight of 17 kilonewton per meter cube. Angle of intersection is 30. So find out. So first find out the active earth pressure and passive earth pressure coefficient. So K is equal to the 10 to the 45 degree minus 5 by 2, which is equal to 1 by 3. So Kp is the 1 K by the 1 by K, so which is equal to 3. Now K minus Kp minus K is equal to K, which is equal to 2.67. Then found out the PA bar and PP bar. So first see the figure. Here is the figure where H is given 6 meter and we have to find out, and gamma is 17 kilonewton per meter cube and phi is 30. And the right side figure, that is figure B, is the pressure distribution diagram of this problem. You can see that in the right hand side equivalent pressure is acting along the point row or point of zero share. Uh, and in the left side is acting as a passive earth pressure. So PP you have to find out. Uh, PA bar you have to find out, which is equal to gamma HK, which is 17 into 6 into 1 by 3, which is 34 kilonewton per meter square. Now we have to find out the Y naught. Y naught is equal to the PA bar divided by gamma into Kp minus K, which is equal to 0.75 meter. Now PA force, earth pressure force, half into PA bar into H plus half into PA bar into Y naught. So we put all this value and it is equal to the 114.75 kilonewton per meter length of the wall, and it is we approximately equal to the 115 kilonewton per meter. Now find out the passive earth pressure. So passive earth pressure is equal to PP bar, which is equal to gamma into D into Kp minus K minus PA bar. So D value we have to find out. So the equation is, after putting all this value, the equation is 45.4 D minus 34. Now PP bar dash is equal to the gamma H Kp plus gamma D Kp minus K, after putting all this value, and this also come out in terms of D after putting all this value, which is equal to the 306 plus 45.4 D. Our main target is to find out D, and then PP double dash bar, which is equal to gamma H Kp plus gamma Y naught Kp minus K, put all this value and it is become 340 km per meter. Now to find y bar, we use this equation, which is equal to PA y bar is equal to the half PA bar h by into h by 3 plus y naught plus half PA bar y naught into 2/3 of y naught. Now put all this value, which is equal to uh, y bar is equal to 2.5 meter. Now to find out uh, D naught first. So to find out D naught, we put all this value in this equation, which is D naught to the power 4 plus C1 D naught to the power 3 plus C2 D naught to the power D naught square plus C3 D naught plus C4 is equal to 0. where C1 is the PP bar, double dash bar by gamma K. C3, C2 is the 8 Pa by minus 8 Pa by gamma K. C3 is equal to minus 6 Pa by gamma K whole square into whole into 2 y bar gamma K plus P P double dash bar. C4 is the minus 6 Pa y bar into PP double dash bar plus 4 Pa square divided by gamma K whole square. Put all these value. And find out the D naught, which is equal to the 5.3. And we know that D is the D naught plus Y naught, which is equal to the 6.05 meter. Then for design purpose, we increase the D about for 20 to 40%. Consider we assume we increase it 40%, that is 1.4 times. So it is equal to 8.47, approximately 8.5 meter. So after that, now find out the section modular. Before we find out the section modular, we have to find out the y naught bars, which is equal to the root over 2 Pa divided by gamma into k, and which is equal to 2.25 m meter. Now maximum moment, which is equal to the Pa into gamma bar into y bar plus y naught bar minus 1 by 6 y naught bar cube gamma k. Put all this value and it will become 460 kN meter per meter. Now section modulus is equal to the mx by fb, where mx is 460, fb is the 175 into 0.3, so which is equal to the 626.25 into 10 to the minus 2 meter cube per meter of 1. Now I think this problem is clear to everyone. Now move on to the next problems. Uh, I think the sheet piles are over now. Uh, we have to check the now in lecture number 49 we have now discussed about the anchor bulkhead. So anchor sheet pile walls or anchor bulkhead are a type of retaining wall found in waterfront construction which is used as warehouse or piers for loading and unloading ships or barge. The construction of such walls is accomplished by first driving the sheet piling into soil to a desired depth and then attaching a tie rod support at the upper end of pile and anchoring it to concrete blocks, raised piles, or other means of support located at a point safely away from any potential slip surface. So these are the arrangements of different types of anchor bulkheads. You see that there is a we use and there is original ground and there is a final ground, and we use as a different types of now anchor bulkhead sheet pipe. So these are the working mechanism figure. So there are active wedge, passive wedge, dredge level, deflected shape of the wall, and there is anchor. And this condition for free arch support of an anchor bulk. So it is said that if the sheet pile have been driven to a shallow depth, the deflection of the bulkhead is somewhat similar to that of a vertical elastic beam, whose lower end is simply supported and other end is fixed as shown. A bulkhead which is safety from this condition is called as bulkhead with free arch support. These are the working mechanism. It's a pressure distribution of this system. Then, if the sheet piles are driven to a considerable depth, the lower end of the bulkhead is practically fixed in position because resistance to the soil adjusting the end does not permit more than a significant deviation of the wall from its initial vertical position. Therefore, anchored sheet pile walls of this type will be called as bulkhead with fixed arch support. Compute the minimum depth of embankment based on the equilibrium and increase the value by 20 to 40% is given a factor of safety of 1 to 2, 1.5 to 2. The alternative method to apply the factor of safety to KP and determine the depth of embankment. Where these are the calculation, you can go through it to solve the problem. Now, move on to the lecture number 50, which is also for bulkhead, and there is a deep foundation excavation. I think up to this, let's stop here. So, so I think the time is over now, and these topics, this lecture number or week number 9 and 10, I will specifically discuss in another lectures, extra lectures, which is going to be held on 14th April, and time is from 6 to 4 to 6, same timing. And what and I am also discussing the problem of these weeks, which is week number 9 and 10 in this extra session. So don't worry about this. also discuss the assignment problem on this week on this extra class. So because of I'm traveling, so because of this, I am not able to access or I am not solving the assignment problem or exercise problem. But I think whatever I am discussing today, it is sufficient for this topic. Um, if anything remains, I will solve or I will teach you in this extra session, which will be conducted on 14th April. So be prepared and try to solve some problem by yourself. And I am sharing the previous year solution also. You can go through it. Now it is the time to close our session, and it is already 6:07. And if anything, any doubts, you have any doubts, you can discuss uh, uh, in my next session. We can discuss. So tell me in next session. So it is already. So don't worry. Or these lectures are recorded and it will be shared to you in my YouTube channel. Materials also share my will be share my Google Drive. Don't worry. I am stopped now. So thank you everyone. I will meet in the next class next week. It is week number 11. We have remained only 2 weeks. Week 11 and week 12. After that, there is one extra session on 14th April, immediately after the week 12, which is on 13th April. And up, by the time you revise your whatever I am discussing, now there is the part two or three topics are remain, and these are not as much as important, which I am discussing in the previous classes. So these are extra. So you more focus on the previous classes. Most of the answer questions will become from the previous classes. So main focus will be on your previous classes lectures. So thank you. I'm stop here. So we will meet in our next week. So thank you everyone. Good night.